Okay. An important concept in this whole discussion for the RLC circuit is called impedance. Impedance. You know, if I have a simple circuit with only one resistor in it, I can apply Ohm's law to it. V equals IR. Now I have a complicated circuit with R, L, and C. We put everything in a black box. No, it doesn't even have to be RLC in series necessarily. Just a whole bunch of elements are consisting of R, L, and C. I hook up to a power supply, right? The amplitude of the EMF is V maximum, and the amplitude of the resulting current is I maximum. Instead of Ohm's law, which is V equals IR, now I have V maximum equals I maximum times another constant Z. So that Z is like the effective resistance, except when there are L and C involved, not just R, I don't call it resistance anymore. I call it impedance. So the impedance, what is that equal to? Well, if it's an RLC series circuit, we already did that calculation, right? We found, I maximum equals Z maximum divided by this guy. So therefore, the impedance value for an LRC series circuit is the square root of R squared plus omega L minus 1 over omega C squared. This is only valid for an LRC series circuit. Okay? If I put LRC in different order, not all in series, the value of Z can change. The impedance can change. But the idea, the definition remains the same. Okay? It is a ratio of the EMF amplitude and the amplitude of the resulting current. Now, we're not limited to only LRC circuit in series. We're now going to take a look at a couple of different examples with the same idea of phasor. Here is a filter circuit. It consists of only R and C. You can also put R and L if you want to. It is not powered by a DC battery, because that way I just have a charging and discharging current, which we studied long ago. This is powered by an AC power source. We call it input. Okay, what I want is an output voltage, which is the voltage across the resistor. I want to see what kind of output I'm going to get based on this input. Okay, so what I'm looking for really is the amplitude of the output voltage versus the input voltage. How do I do that? Well, this really is an RLC series circuit minus the L. Okay, so I have the amplitude of the current. I already know how to do that. I maximum equals what? V maximum, or in this case, I'm going to just write V in. Okay, for the amplitude of the EMF here, divided by Z, right? Z. This Z, I know how to calculate that, except in this Z there is no L. Okay, there is no inductance. So it's V in divided by the square root of R squared plus, what do you have left? Omega L minus 1 over omega C. But there is no L, so it's just 1 over omega C. That's it. Squared. Given I maximum, I can find V out, which is the amplitude of the voltage across the resistor. So V out really is just I maximum times R, Ohm's law applied to the resistor, and therefore the ratio of V out over V in. Okay, the amplitude of the output voltage versus the amplitude of the input voltage, I can write it now. V out, which is this guy times R divided by V in, so V in and V in cancels. It's R divided by the square root of R squared plus 1 over omega C squared. Okay? Now, this expression depends on omega. Let's take a look at what happens when omega is really large or really small. Okay? You look at a really low frequency signal, omega is very, very small. So therefore, 1 over omega C becomes really, really large. It dominates over R, so this whole expression, approaches this whole expression just approaches 1 over omega C. Okay, so let's see what it approaches to. The denominator becomes 1 over omega C, and then you flip it over, it's just R times omega times C as omega, which approaches 0 as omega approaches 0. Okay, so the output signal reduces to 0. And yet, on the other hand, when omega becomes very high, okay, 1 over omega c is very, very small. So you can ignore that. R over R, you just get 1. So it approaches 1 as omega approaches infinity. So you see, the output signal becomes very strong when the frequency becomes high, and it becomes very weak when the frequency becomes low. So suppose you have an input signal which is a mixture of a whole bunch of frequencies, including high frequency component and low frequency component. Okay, as you go through this filter circuit, you take out, you only read V out. Then for the low frequency components of the circuit, the output is really small. For the high frequency output, high frequency component of the input signal, the V out is very large. It basically, is almost 100% of the signal, of the high frequency signal. So this is a filter circuit, in a sense that when you have both high and low frequency components in the input voltage, only the high frequency signals are allowed to pass. The low frequency signals are blocked by the presence of this capacitor. Okay, so this is a high pass filter. You will read mostly high frequency signals, and the real low frequency signals are just blocked by this filter. So it filters out low frequency signal. Why does it do that? Well, qualitatively, you can understand what's going on, because a capacitor is happy when the frequency of the signal going through it is high, because it goes through a rapidly charging and discharging cycle. There is never enough time for Q to accumulate, and therefore Vc would be almost equal to 0. It's very, very small. So you can replace it by a wire almost, okay, at high frequency, and therefore, of course, effectively you only have the resistor. Only one resistor, nothing else. Then of course V out is almost equal to V in, which is what we get. On the other hand, when omega is really, really low, you can imagine that you can imagine what happens. You have a very long time to charge it, okay, and then it's very slow to discharge it, and it takes a long time, okay, to build up a lot of charge. Therefore Vc becomes very large. It dominates over Vr. Very little current flows through the resistor, and therefore V out is also very small. So that is an example of a filter which filters out low frequency signal. You can also design a filter that filters out high frequency signal. Guess how do we do that? Instead of capacitor, what do we do? You probably have guessed. Yeah, put here inductor instead. Okay, because the inductor doesn't care about low frequency signals. It just let it pass as if it's just a wire. On the other hand, if you try to drive a very high frequency signal through it, it's unhappy. It puts a lot of fight, and therefore a low frequency signal can easily be picked up here. The high frequency signal is blocked by the inductor. So these are called filter circuits, and we utilize the dependency of the voltage on the capacitor and inductor on the frequency of the signal. Now, another example that I want you to go over with you. You don't always necessarily have to put RLC in series. Okay, you can put these elements in whatever way you want, just like what you do with a DC circuit with only R's. You can put a whole bunch of R's or a whole bunch of C's in different order. And if you put RLC not entirely in series, you're not going to get the same impedance that we calculated before. So please do not assume that the impedance always has the same expression like you see here. This is only for RLC series circuit. Okay, if that's not the case, such as what we see here, what do we do? This is an RLC parallel circuit. Okay, what is the effective impedance of this circuit? Or we can just say, given the EMF here, the amplitude EMF and everything, given RMC, can you find the resulting current? In particular, what is the amplitude of the current, and what phase angle does it make with the voltage signal? Well, the result would be different, but the idea is the same. That is, we're still going to use the phasor diagram. Okay. Now, in the case of LRC series, we know that everything has the same current, right? Everything has the same current, but you have to add up what? You have to add up the voltages, VR, VL, and VC. that will add up to V, right? Here in our case, do they have the same current? IR, L, and C? Well, there is no reason to say they have the same current anymore, right? But they do have the same what? They will be subject to the same voltage. So everything has the same voltage, but you have different current. Now, instead of adding voltages up for the series circuit, what do I add? What do I add? Well, I have to add the current, right? This total current is a sum of these three currents. So, in a phasor diagram, before what I did was I drew a whole bunch of phasor vectors for the voltages, because then I have to add these voltages up, right? Here, what do I draw instead? Well, I must draw the current phasors, right? Because when you add these three current phasors, what do you get? You should get the current phasor for the total current I. So now I have I equals IR plus IL plus IC. These three elements, they have different I, but they have the same V, okay? They have the same V. So, given the fact that these three elements have the same voltage across them, what about their currents? Do their currents have the same phase or not? Well, you recall that for a resistor, IR and VR, they have the same phase. Okay? For an inductor, VL leads the current by 90 degrees. Remember that? So therefore, this current is going to lag VL by 90 degrees, which means it's also going to lag the IR by 90 degrees. Okay? Because IR has the same phase as V. This guy lags behind V by 90 degrees. What about that one? Well, remember, VC lags behind the current IC by 90 degrees. In other words, the current leads the voltage across the capacitor by 90 degrees. Okay, so for the same three V's, IC must lead IR by 90 degrees. In other words, it must lead IL by 180 degrees. Okay, this is what I have in mind. So, with that clear, I'm now ready to draw a phasor diagram for IR, IL, and IC. You know, IR has the same phase as V, as the phasor for the EMF, but IL would lag behind by 90 degrees, and IC would be leading by 90 degrees, right? So let's draw that. Okay, so what I did was I first have to set VT. Okay, you have to tell it what kind of EMF you're using to power the circuit. It's the same as we did before. V maximum sine omega t. Okay, we always assume the EMF is like that. So let me draw the phasor for the EMF vector, which is which makes an angle omega t from the reference line omega t. Okay, and IR therefore has the same exact phase angle because IR and VR always have the same phase. Okay, now what about IL and IC? You know that IC leads by 90 degrees. Okay, so I'm going to draw IC now. It's 90 degrees away from IR, so it is going forward because it leads, so it's there. I'm going to draw IC like this, 90 degrees. This is IC. Meanwhile, what about IR? Sorry, IL. IL lags behind IR by 90 degrees, so it goes the other way. Okay, so I'm trying to use a different color, but running out of color, so let me just use a green color for IL. Okay, so you see again, IC and IL, they're opposite to each other, just like VC and VL were opposite to each other. Okay, and you have to sum over all these three currents, phasors, IR, IC, and IL, because then you get a total current, right? You're going to get a total current. And again, which two vectors do we sum up first? Obviously, it's IC and IL, because we know they're always opposite to each other in phase. And which one wins? I don't know. Let's assume IC has greater magnitude than IL, and therefore, this would be IC minus IL. Okay, IC minus IL. And then after that, I'm going to add to IR, right? And these two vectors are perpendicular to each other, so I'm going to add them together by drawing this parallelogram, or actually just a rectangle, and I get this resultant current I. That is the current, the whole current running through the EMF. So naturally, you're going to get a phase angle. the current then leads the voltage by a phase angle phi. Okay, I can find phi. I can also find the amplitude of the current. I can find all of these things if I utilize the phasor diagram. Let's see how I can do that. Okay, first of all, what is the amplitude of the current equal to? Okay, what is the amplitude of the resulting current? Well, the amplitude of this guy is what? Is V maximum divided by what? Divided by R, right? Because this is Ohm's law. Okay, this is Ohm's law. This is the current running through this branch. Okay, the amplitude of IC is what? Remember the reactance. Okay, it is always V maximum, which is the voltage amplitude applied to this capacitor, divided by what? Divided by XC, right? The reactance. Okay, what's the reactance? XC is 1 over omega C. So I have IC, that's the amplitude of the current going through the capacitor. It is equal to the voltage amplitude going over it, that's V maximum, divided by XC. XC is 1 over omega C. So this is omega C times V maximum. Okay. Meanwhile, I already know how to do that. That's Vm over R. And then IL equals V maximum divided by XL, which is omega L. So this V maximum over omega L. Again, you'll notice that all three elements have the same V's. Okay, they're all powered by the same exact EMF. So V maximum, V maximum, V maximum. All right. Now, I'm going to apply the Pythagorean theorem for this right angle triangle. So I have the amplitude squared for this vector. That is I maximum squared, right? I maximum is the amplitude of the resulting current, equals what? This thing squared plus that thing squared. Okay, this is, what is the magnitude of this guy? Right here, right here. V maximum over R. You square it, right? Plus that amplitude squared. Okay, and that is equal to IC minus IL. IC is right here, IL is right there. So it's omega C V maximum minus V maximum over omega L, and then square it. Right? So I'm now able to calculate I maximum just by taking the square root. So I maximum equals to V maximum, which is just common factor which I take out, times the square root of what? 1 over R squared plus omega C minus 1 over omega L squared. So, what is the impedance Z of the circuit? By definition, impedance is defined as V maximum over Z, right? Current times impedance always equals to the amplitude of voltage. So Z, in this case, is the reciprocal of this expression, which is 1 over R squared plus omega C minus 1 over omega L squared. You see, it is totally different, okay, from the expression that we obtained for LRC series. This is Z for LRC parallel. So please do not take that formula for granted. It changes as the circuit changes. Okay. Now this is reminiscent of how we calculate the resistance for three branches in parallel. Remember how we did that? 1 over R equals 1 over R1 plus 1 over R2 plus 1 over R3. See, something similar. Okay. Now you flip that over, you get 1 over Z. So 1 over Z equals instead of 1 over R1 plus 1 over R2 plus 1 over R3, I have to. It is reciprocal, but I have to do some sort of a square root addition, and that is again because of the phase difference. Okay, the currents IR, IL, and LC, they do not have the same phase. Okay, they do not reach maximum minimum simultaneously. This is what makes the phasor diagram particularly useful. So please make sure you know how to apply the phasor diagram to different cases. You know what phasor to draw and how you add up phasors. Like in this case, we have to add the current phasor. In the series case, we have to add the voltage phasor. Okay, now how do you find this phi, the angle phi, the phase angle? Well, again, Tangent phi equals this over that. So I'm going to I am going to write down the formula for the phase angle. Okay, the formula for the phase angle. Tangent phi equals what? This over that, which is IC minus IL over IR, right? And we can easily plug in the values of IC, IR. Right? So this is omega C. There is a Vm in every term, so I'm going to throw that away. Minus what? 1 over omega L and divided by R. You see, there's something interesting about this combination. We've seen something similar to it before, but not exactly. Before we had omega L minus 1 over omega C. Now it's omega C minus 1 over omega L. Okay, so this it's actually, I'm sorry, it's not R. It's IR is V maximum over. So this 1 over R. I'm sorry. Okay, 1 over R. All right. So be careful about that. It is equal to R times omega C minus 1 over omega L. Okay, but just like before, when we set these two terms to be equal, I will get a certain value of omega, which, as you know, before we call it resonance frequency. Here, something similar. At omega equals omega naught, which is the square root of 1 over LC. You know this expression is again equal to 0. Okay, then I have phi equals 0. What is the significance of that? What's the physics behind it? Add this frequency. Okay, look, add this frequency. Omega C equals 1 over omega L. And going back to here, going back to omega C equals 1 over omega, that means IC and IR have the same what? They have the same magnitude. Okay, they have the same magnitude. Now, the thing about IR and IC is that IC and IR, they're always opposite in phase. So when wind flows, when the current in the capacitor flows this way, at the same moment the current through the inductor must flow backwards. They're always 180 degrees away from each other. And at that particular frequency, they also have the same magnitude. So you add IL and IC, okay, the actual current, not the phasors, but the actual current. Add that frequency. What can you say about the total current, IC plus IL? Well, they flow in the opposite direction and they have the same magnitude. So add up to what? To 0, right? So in that particular case, there is no net current flowing through L and C. You can ignore these two branches as if the only branch that's left is the current. Okay? So it becomes a purely resistive circuit once more, with IL canceling with IC. So it's as if the current, as if the inductor and capacitor do not exist. And no wonder phi is equal to 0. Okay? Because again, phi is the phase angle between the total current and the current in the resistor. At that angle, there are no net current for IC and IL. So the total current is the current going through the inductor, right? Going through the resistor, because these two branches have no net current flowing them. Total current just flows like this. It only flows like this. Okay, so the angle phi, no wonder it's equal to 0, because these two vectors are really the same vector. Okay, and this is also where you have a peak value. You have a peak value for I maximum because the of the fact that these two terms cancel out. Okay. So if you look at the impedance, when these two terms cancel out, you have the smallest possible value for the denominator, which is just 1 over R. You flip it over, Z becomes R. Okay, that's as small as the impedance gets. So you have the largest possible amplitude for the current. So that is the resonance. So strangely enough, even though this is the RLC circuit in parallel, the resonance frequency still is the same. It's given by the same expression. But instead of VR canceling with instead of VC canceling with VL, this time I have IC canceling with IL. But the effect is the same. The only thing that's effectively left is just a resistor. It becomes a purely resistive circuit with largest possible current and the smallest possible impedance, which is just equal to R, because after all, these two guys just cancel themselves out. Okay, so there are countless other ways to connect R, L, and C together. We studied the two simple common cases of all three in series and all three in parallel, but my message here is that these results are not as important as the idea. The idea is to use phasor, the phasor diagram. Okay, by defining phasors, we can add, instead of adding the whole bunch of sine functions together, we can add these phasors up vectorially, which is easier to do. And for different circuits, we have to draw different phasor diagrams and know which quantities to add. Okay, so to sum up that problem, to sum up the LRC parallel circuit, we find that the resulting current I, in response to the EMF, the resulting current I should go like this: I maximum sine omega t plus phi, where I maximum again is given by something we just calculated. Okay, I maximum is again given by this expression, V maximum over Z, with Z given by that, and phi given by that expression. Okay, so we have successfully solved this problem. We found what kind of current will result when you put all three elements in parallel, powered by a certain EMF.